it's important to remember that with recursion, you are always going to have to trace the code to actually see what's going to happen. You're not just going to be able to look at it most of the time and know whether it's correct or not. When it comes to writing recursion, the thing to remember is that it should be 2 steps. You always must have a base condition, which is how you're going to exit the program, or exit the recursion, and then you must have a recursive call, which moves you 1 step closer to that base condition. If you don't have a base condition, you have infinite recursion. If you don't make the recursive call go closer to the base condition, you have infinite recursion. So those are the 2 most common mistakes. Beyond that, remember to just add some print statements so that you can see what's happening or trace it out on paper. Never be afraid to pull out a piece of paper and trace it, which is what we're going to do here for one of these examples. So why are we using recursion and why do we teach recursion? Well, there are many places where you can do either recursion or a loop. And quite frankly, they're usually about equivalent. Sometimes recursion will just make more sense in your head because of the particular problem, but sometimes a loop will make more sense in your head because of the particular problem, and either is okay. But there are cases where realistically the only viable option is to do it with recursion, or at least it becomes incredibly complex to write the code without recursion. And usually those types of questions come down to being non-linear. What I mean by that is an array is linear. It's a line. You're going to do something that walks down the line. But imagine something where you're doing something on half the data or a quarter of the data at a time, and you're going to need to branch off in different directions. Those are going to be cases where you're going to have to probably use recursion because it's really hard to keep track of where you are. So there's 2 examples that were mentioned here on this slide. The first is, let's imagine I asked you to write a program to look through your entire hard drive and tell me if it found a file. So when you're in Windows or Mac, doesn't really matter, you have a file finder of some form or a file explorer. And you have folders, and folders can contain folders, which can contain folders, which can contain files. You can have files all the way up and down. So if I asked you to write a program to go through and find a particular file or tell me that it's not there, how would you do that? Well, if we think of a loop, you might start off at the root, or it might be /home/ your name if you're on a Mac, or it might be C:/ if you're on a Windows machine. So you'd start off at some part of the file system, and then you would check to see, is the file in that directory? That's easy enough. So go through and you say, is this the file? Is this the file? Is this the file? No? Okay, great. That might be a loop. But then you also have to check every one of the folders in there and go to all of the files that are in all of the folders in there. So how would you do that? Well, you'd have to have a separate loop that says, if there's a directory or a folder, then I need you to go into the folder and check everything in there. But if there's a directory in there, you'd have to have another block of code that says, okay, well, if there's and how far down does that go? I think you can quickly see that you'd have to have a lot of code to deal with how many different layers there might be in the file system. So it's not particularly trivial to do that with a loop. I'm not saying it's impossible. You could absolutely code it. It would be pretty ugly. A simpler solution would be to say, is the file in the current directory by comparing all of them? And then for every subdirectory that you have in your current directory, recurse. That's it. Now your recursive function is going to go check the top directory, and then take the first folder, recurse into it, check all the files in there. If there's any folders in there, recurse into them, check all the files in there, check all the files in there, and so on and so on and so on, all the way down the file system. So that simple block of code will do that recurse for you, and we're going to look at that in just a moment. Another example where recursion is a very helpful thing is if you were writing a game and you had a 2D array that was your board. So you have a 2-dimensional array, and each cell represents one place that a character can be on your board. And you wanted to see if there's a path for that character to get out. So, the example that frequently comes up is you have a mouse and he's trying to find his cheese in a maze, but it may also be that you have, a character who's trying to find their way out of a set of tunnels or whatever it might be. So the maze might represent the actual board, and certain pieces of certain cells in the array might be blocked, and maybe you represent those by you storing a character in those that's an X or a pound sign that says you can't go there. So how would you find your way out of that programmatically? Well, The answer is you see if you're already at the exit. If not, you try going north. If that works, great. If it doesn't, then you try going north again. And if that doesn't work, then you try going north again. And once you reach a wall or you reach the edge of the maze, then at that point, try going right. So instead of writing that out bit by bit, what you would actually really do is you would write something recursively that says something along the lines of, am I at a wall or am I at the edge of the maze? If neither of those things are true, then at that point, recurse north. And you also need to check if you found your goal. That's going to be your base condition. Did the mouse get to its cheese? Yes, return true. No, then we're going to recurse north. If that doesn't work, then we'll recurse right. If that doesn't work, then we'll recurse south. If that doesn't work, we'll recurse left. And if that doesn't work, then we didn't find the cheese. There is no cheese, or there's a wall in the way, or something bad has happened. But that's a relatively small amount of code to do something very, very complex. Now, it's going to take a while for it to do that, especially if you have a big array. And I'll actually show you an example of that in just a moment. All right, so let's take a look at anything that is nonlinear. You're probably going to want to write recursive. The example of the folders inside of the folders is nonlinear because you don't know how many nested folders you may have all the way down. It may be that you only have one layer of folders. It may be that you have hundreds and hundreds of layers. And if you think of your file system on your computer, you'll probably quickly realize that there are many, many, many layers of those things, of those folders. So how does it keep track of where all that is? Well, that's what the stack, the activation stack that we looked at 2 lectures ago is all about. We're going to do another example with an activation stack just so that you can remember how that works. All right, so a common test question that you might get, or a quiz question, will be you're going to be given some block of code that looks perhaps like this, that's recursive in nature. And at a quick glance, how do I know that it's recursive? Well, I look at the name of the function, which is do work, and right here in the middle of the function, I have a call to do work. That tells me that the function is calling itself, therefore it's a recursive function. Now what's interesting here is you can actually see that I'm calling myself twice, and that might seem counterintuitive, but there are circumstances where you would want to do that. If we talk about the maze example that we just talked about a minute ago, where you're trying to have the mouse find the cheese, you'll actually probably have 4 recursive calls. 1 for north, 1 for west, 1 for south, 1 for east, or up, down, left, right, whatever you want to call them. So it's not unusual to have more than 1 recursive call depending on what it is that you're trying to do. If you're going into the folders, you'll actually have as many recursive calls as there are folders. So you might actually have a loop around a recursive call, which sounds crazy, but that's also a possibility here. All right, so we're going to take this block of code and we're going to trace through it. You'll notice that at the bottom, we are supposed to call do work with the number 4. So what I did was I made an array, a spreadsheet, and I just laid it out so that it might be a little bit easier to follow along with. Okay, so we begin with do work 4, which is apparently being called in our main function. So our main function got added onto the stack and it called do work 4. That's what we're presuming. So do work 4 gets added onto the stack. And I copied in the code just so that we can trace it directly in here, and also so that I can highlight. Any print statements that come up, I'm going to print down into this box down in the bottom right-hand corner. So that's why I have that, which of course my little window will be in the way, but I'll move it when we get there. All right, so we're going to start off, and it's going to say do work 4, and it's going to pass a 4 in, which is going to be called an integer called I inside of this method. So the very first thing that happens is it's going to print I, which is 4. Okay, now here's what I'm trying to get across by doing this, because we've seen where people have traced code before. I need you to get over the idea that there are some people in the world who could just look at this and tell you what the output is going to be. I cannot tell you what the output of this is going to be just looking at it. No one can, because recursion means you're going to have to walk through it bit by bit. So if you get a question like this on a test or on a quiz, you need to actually trace it out, just like I'm doing here. Obviously, you can do it on paper instead of in a spreadsheet, or if you're on a test, you can use the answer box to make notes as you go through it, and then just erase the notes when you're done and only leave the answer in there. But you need to trace it. Don't try to just jump ahead and see what's going to happen. So we're going to do this line by line. So to review, I had just done this print statement. And what I'm going to do is I'm going to mark it red just so that we know that it has been completed. All right. Is 4 greater than 2? Yes, it is. So we are going to make a call to do work with I minus 1. So I'm going to mark those as red because I'm about to be done with them. And do work minus 1 is do work 3. So we're going to make a new copy of the method. Stick that up here. And I guess I should have everything back to being in black again. You know, it would have been great if I had copied this when it was black to start with. There we go. Let me do that so that I don't have to keep doing that. Great. Okay, so note that this method has not completed, right? It is still on the stack. There is still work for it to do. I have made this call, which immediately forced me up here where I have a new instance on the stack, but there is still stuff to be done in this method as well. So that's why I'm using the coloring, because it's important to note which things have actually been done. All right, so we come up here and we start do work 3. So I is 3 this time, and we're going to print out I. So that time we're going to get a 3. I'm putting spaces in. I know that they're not really there in the code, but I just want to make sure that it's easy to read. Yeah, my little window's already in the way. I think it has converted that into a date because spreadsheets. Fantastic. All right. So the print statement has happened. Life is good. We're going to mark him as red. And is 3 greater than 2? Yes, it is. So what's going to happen is we are going to call... What are you doing, spreadsheet? Really? There's some comedian who says that, you know, in Microsoft Word, when you hit backspace once and you expect it to do a very simple thing, and then in reality what happens is every block of text on the page suddenly gets reformatted, and vaguely in the distance you hear sirens. I think that's a very accurate description of how spreadsheets and things sometimes work. Okay, so now that I have put the world back together again... Oh, good Lord. Okay, I'm just going to paste the entire thing again. And the worst part is I hit copy instead of paste. Well, this is going splendidly so far. I thought this would be easier than writing it. All right, silly me. Okay, so to review, we were here in do work, and we had successfully done the print statement. We know that 3 is greater than 2, and we know that we are going to make a recursive call with I minus 1, where I was 3 in this case, so that's going to give me do work 2. Great. So we get our new copy of the method. And again, there's work left to be done in here. All right, so we start this one. I is 2 this time, so we are going to print I, which is going to have the effect of me. Yeah. Okay. Oh, it won't let me type in the window. This is going great. Okay, there we go. Now, could you just format that to be a string? That would be grand, so that I don't have to fight you. Plain text. Thank you. Hey, I printed it too. Okay, so the next question that you have to ask yourself, according to this code, is 2 greater than 2? And the answer to that question is no, 2 is not greater than 2. So it's going to skip over this if statement. So this if statement is now complete. All right, and at that point, it's going to print I, which is still 2. So down in our little print window here, now that it works, we get another 2. Okay, at this point, our method is complete. We have actually gotten to the end of it, and everything that was to be done in here is done. So this method is going to pop off the stack. That was supposed to be a lot more dramatic. It was supposed to actually pop off the stack. Hey, there we go. All right, cool. And so now we are back down in this method down here. So you'll remember the last thing we did here was we called do work at I minus 1. Well, I was 3 in this one, So now we're supposed to do work 3 minus 2, which is 1. So I'm going to mark that we've done this. And now we're going to make a new call to do work with 1. And we get a new copy of the code. Great. So we start off and we do our print statement. And that's going to have the effect of printing out a 1. All right. Now, is 1 greater than 2? 1 is not greater than 2. So it's going to go down and it's going to do the print statement at the bottom. And that's going to give us another 1 in our output. Great. And at this point, everything that's up here has now been done. We did everything we were supposed to do. So this method has completed. And at this moment, this method is going to pop off the stack. And that's going to pop off the stack. And we're going to be back down to this one again. All right. So we did this, and we have reached the end of a curly brace. That's fine. The next thing to do is we're supposed to print I. I, in this case, is 3. So we're going to add a 3 onto the end of this. All right, and that means that that print statement is now done. The curly brace is done as well. I think you get that idea. And so you can see everything in this method has been completed. So, like everything else, this method is going to pop off the stack, and we're going to come back down to here. Where we left off here, we had called do work of I minus 1. Well, I minus 1 is done. So now we're supposed to do work of I minus 2. Do work was 4, so that means I'm going to call do work of 2. All right, and I'm just going to mark that as being complete because we have actually made this call. Great. So we're going to start our work again. We're going to print I, which is going to have the effect of printing a 2. And now we're going to look at, is 2 greater than 2? And the answer to that is no, it is not. So we are done with everything down to the print statement again. And we are going to print out I, which again in this case is 2. Okay, and that means that the print statement is now done. And we are now done with this method because everything that was supposed to be done is done. So that method's going to pop off the stack, and we're going to return down here. We had done this last time, so now we're going to come down and do the last thing, which is to print I, and that should be a 4. And then that's going to get marked as being done because we have completed that. Everything in this method that was supposed to happen is done, so this is going to pop off the stack, and we go down to our main, and we would continue on with whatever was the next statement after do work. So hopefully that was helpful. I need you to get, I know I was wrestling with formatting and silliness in a spreadsheet, and maybe a spreadsheet's not the best way to do this. Normally I would have just drawn it, but I thought this might be an easier way to do it. Yeah. But anyway, if you are, if you're following along, the important part of this is you need to draw it out and actually see what's going to happen. Because the output of this was 4, 3, 2, 2, 1, 1, 3, 2, 2, 4. And at a quick glance of that code that was in there, I don't think you would ever have come up with that. And if I had said trace it with do work 5, you'd have a whole different output again. Because of the print statement being after the recursion, you're going to get numbers that are big towards the end, and you just have to trace it. There is no way you can look at that and tell me that that would have been the output correctly. So the lesson here is take your time and trace it. It's a very important lesson in general for computer science. Anytime you're dealing with some larger structure that you can't necessarily visualize, you just have to trace it. Recursion, always trace. Data structures, which we're going to see in a couple of weeks, you're pretty much always going to have to trace them as well. All right, so 4, 3, 2, 2, 1. If we go on to our next slide, 4, 3, 2, 2, 1, 1, 3, 2, 2, 4. Yay, we got the right answer. And then, of course, we have very clever, the matrix has Unio. Somebody was having a lot of fun writing this slide. All right, so that is how you would go about writing something, or how you would trace something. Let's talk about how you would go about writing something. All right, so you might remember that Fibonacci, which is one of those weird things that only ever comes up in computer science. It's a wonderful little idea where somebody was tracking the reproductive methods of rabbits because they were very bored. If you start off with 2 rabbits and every rabbit matures within a month, and you put 2 rabbits into a cage to start with, at the end of the month, you will have more than 2 rabbits. And if you continue to leave all of the rabbits in this cage, which we presume is a large and happy cage where they can roam around freely, then you'll get more and more and more rabbits. As a matter of fact, it grows very, very quickly. So that's what Fibonacci is. Very exciting stuff. So if you were to write Fibonacci recursively, how would you go about doing that? So there has to be a base case. I should explain what Fibonacci is, huh? All right, so in the base case, the first 2 numbers in the sequence. So if you ask for the Fibonacci is 0, you get 0, because if you have no rabbits, then you still have no rabbits. But if you have 1 rabbit and 1 rabbit for the first 2 months, then in the next month you will have 2. The way that you get to that number is every number in the sequence past those 2 ones is going to be the previous 2 numbers added together. So this one is 2 because of 1 and 1. This one is 3 because of 1 and 2. This one is 5. I hate computers today. This one is 5 because of 3 and 2, and this one's going to be 8 because of 3 and 5, and this one's going to be 13 because of 5 and 8, and the next one's going to be 21 because of 13 and 8. So every number in the sequence is the sum of the previous 2 numbers. And the reason that you might immediately think of recursion here is because you have a base condition. If you ask about the first 2 numbers in the sequence, the answer is 1. For every other number, I need you to calculate the previous 2 added together. And of course, to calculate the previous 2, especially when you're up at numbers like this, they're going to have to be calculated themselves based on previous numbers and so on and so forth. So the code for this actually ends up being very, very simple. So let's take a look at our solution. So we have a static int, which is going to return an integer called fib. It's not a lie. And it's going to take in an I, which is the particular number in the sequence that I want. So if the I is 1, I return 0, because there's none. If the I is 2, then I'm going to return 1. In every other case, I'm going to return the Fibonacci of the number before and the Fibonacci of the number 2 before that, and we're going to see what happens. So let's do this one with a drawing instead of trying to do it with the spreadsheet, because the spreadsheet didn't work out so well, as we noticed. All right, so we'll use the magical drawing board. Okay, so we have this code, which is fib. We're going to draw a stack. Here's our stack, and we're going to have our main. Get to watch my handwriting this time instead. It's so much better. And we're calling fib of 4. All right, so fib of 4. Could I magically get the code and the window next to each other in a way that you could see both of them? I don't know if I got my big head out of the way, maybe. Hey, okay, there we go. All right, so fib of 4. And maybe if I move this over, no, I will not move that over because reasons. Okay. Would have totally said I could resize that, but it doesn't let me in this size apparently. All right, so fib of 4 is I, which is 4, equal to 1. The answer is no, it's not. Is it equal to 2? The answer is no, it's not. So we are going to call the fib of I minus 1, which is going to be 3, plus the fib of 2, because that's what it tells us to do over in the code over here. All right, so that's going to cause us to have a fib of 3 call, which I'm going to write out here just so I have more room. Okay, so just in the spirit of marking what I had done, I am doing this when I got called. Okay, so back up in our new method, we know that fib of 3 is going to start off and it's going to say, is I equal to 1? It's not, because it's 3. Is it equal to 2? No, it's still not. So we're going to make a recursive call to fib of I minus 1, which is going to be 2, and fib of I minus 2, which is going to be 1. All right, and again, how did we get here? Well, this was what I was asked to calculate, so that's going to make me go to fib. That's a fib of 2. And here's our happy little fib of 2 next to a happy little tree. All right, so fib of 2, we are going to start at the top and we're going to say, is I equal to 1? It's not. Is I equal to 2? The answer to that is yes. So this is going to return a 2. All right, I'm sorry, it's going to return a 1. What am I saying? I said fib of 2. All right, why am I saying it's going to return a 1? Because over in our code over here, if I equals 2, which it does, then we are returning 1. So down in the previous stack where I had fib of 2, that was underlined in red down here, this guy right here, let's use a different color, this guy right here, that has resolved to an answer. And the answer that it resolved to was the number 1. So I'm going to erase this over here because I can, and I'm going to fill in the answer that we just got, which I'll do in green for no apparent reason, which was 1. All right, and that has popped off the stack because it has completed, because it did everything it was supposed to do. So back in fib of 3, I have a 1, plus I'm supposed to have the fib of 1. So that's going to make a new recursive call. Fib of 1 is going to pop up here onto the list. And so fib of 1, if I equals 1, it does, so that's going to return a 0. Okay, and then there's nothing else to do because the if statement, this is the case that just happened, and since that's an if statement and everything below it is an else if and an else, this method is going to return the value that I gave, which is a 0. And since that is a 0, that is going to get filled in here, which is where this recursive call came from. So I'm going to erase this recursive call and all of my scribbles, and I'm going to fill in the number 0 because that's what I got told to do. All right, and this guy is going to pop off the stack. Okay, so fib of 3, when we were in that method, 3 was not equal to 1, 3 was not equal to 2, so fib of 3 was this. And you'll notice that I have now calculated the answer to both of those. I am now left with return 1 plus 0. Well, that's easy to do. 1 plus 0 is 1. So this method is going to return 1. Great. And this method was originally called from down here in the fib of 4 stack. So I'm going to take that and I'm going to fill it in. So fib of 3, we now know to be equal to the number 1. All right, so this pops off the stack because it's done everything it needs to do. Life is good. Just clean up the stack a little bit there in general. Get rid of that line as well. Okay. So now the next thing that was supposed to happen is that we were supposed to calculate the fib of 2. So that's going to make a new call, fib of 2, and that's going to pop up here, and it's going to go look at the code again. If 2 equals 1, it does not. Else if 2 equals 2, it does, so that's going to return 1. So this guy is going to give us back a 1. And that's going to fill in down here because that's where we were originally called. So we're going to erase the call and we're going to replace it with the number 1. There was a plus sign there that I just erased for no apparent reason, and we got back a 1 from there. So the fib of 4 is equal to 1 plus 1. This has popped off the stack, the fib of 2, because that got done. And if we're back down here in our fib of 4 call, we can see that we now have 1 plus 1, which, as you know, is 2. So this guy is going to return the number 2. And since that was originally called down here in main, main is going to return, or it's going to get back, a number 2 for that. And then this guy is going to pop off the stack. So again, this was not the prettiest view, though it did work better than the spreadsheet maybe. But ultimately what happened here was that we found that the 4th number in the sequence is going to be a 2. And if we continued doing that, you would see there'd be an awful lot of calls in that sequence. As a matter of fact, as this gets larger and larger, you're going to see more and more and more calls. So let's do this in our replet window, just so that you can see what's going on. And we're going to do this guy in Java. I promise I'll do the later examples in C++, in C#. So here we go, creating a new replet. And we're going to do this guy in, I'll just copy the code, and then we'll see what we need to fix. All right, so in our main method here, we're going to stick that guy in there, and he'll need to be a public static. Oh, he's already static. Great. Int fib. That looks reasonable. That all looks reasonable. I actually think that's just going to work. Let's see. So we would call it fib of 4, and that should return back an integer. So we'll call it answer equals fib of 4, and I'm going to grab this system.out.println. I'm just going to steal it and print out the answer. The answer here is going to be answer. Cool. Let's run it and see what happens. Chug, 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 chug. Hopefully we get back the answer 2, because that's what we got when we traced it out manually. Hey, it compiled. Answer is 2. Would have been nice if I put an extra space in there, but all right. So just for giggles, I'm going to add a print statement up here. Just so that you can see how many times this method ends up getting called. So every time the method is called, it's going to print I was called with, and it's going to give us the number that it was called with. So we know it was called with 4 initially, and then we know that the 4 is going to cause a call to 3, and the 3 is going to cause a call to 2, and so on, and so on, and so on. So let's see how many times. Okay, so 4 was initially called. Here, that's going to cause a call to 3. 3 in the recursive method is going to cause a call to 2. 2 is actually going to return an answer. So in the previous method, where our I was 3, 3 minus 2 is 1, and so that gives us the call to 1. And then in the previous method to that, the other side of this was a 2. So I want you to understand that the number of times that ends up getting called could grow very, very quickly in this case. So I'm going to ask for the Fibonacci of 20, the 20th position in there. And you're going to realize that the first number that it's going to call in is 20, and then that's going to cause a call to 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2. That one's finally going to answer. But each one of those also is going to have to make a call to calculate each of the previous ones behind it. So as you can see, the number of times that this actually got called is going to be tremendous. So how many times is that actually going to get called? We know that the answer is going to be a lot, but let's actually have some code in here so that we can see it. So what I'm going to do is I'm going to add a global variable effectively. So public static int, we'll call it count, and we're going to set it equal to 0 to start with. And then every time we go into the method, I'm going to increment count. And then I'm just going to print it out. Count is count. There we go. All right, so let's see how many times this method actually got called. And you're going to see a lot. So to be clear, I'm asking for the Fibonacci of 20. And I actually made 13,529 calls to the method fib, which is kind of crazy. And even when we come down to a much smaller number, like our fib of 4, it's still a surprisingly large number of times that you actually have to call it. And it's because you're calculating the answer based on how many, every time you make a call to Fibonacci, it's likely going to have to make another call until it gets all the way down to 1. And annoyingly, it's going to keep recalculating the same numbers over and over again, because after the first path through for 4, it got all the way down to Fibonacci of 1, and then it knew an answer. But it knew at that point the answer to 2. If I went to Fibonacci of 6, you'll see that it's going to recalculate all of these again. I'm just going to put out the value that I was called with so that you can also see that. All right, so we're doing Fibonacci of 6. And my point here is that you're going to ask the same question multiple times. So like right here, Fibonacci for 4 was called, and it tried to calculate it. But then a few moments later, it tried to calculate it again. And like for 3, 1, 2, 3 times it was called. For 2, 1, 2, 3, 4, 5. And as you get to larger and larger numbers, that's going to be a much, much bigger number of times. I'm not going to do it, but if I run Fibonacci for 100, you're actually just going to see this is going to take pretty much longer than you're going to be willing to sit here and wait. It's just going to keep chugging and chugging and chugging and chugging with thousands and thousands of calls. It will either eventually get you an answer, or you will get what's called a stack overflow error or an out-of-memory error. There is a limited amount of memory that your machine has allocated to its stack. If you try to make enough calls, it will eventually overrun the number of the amount of memory that's available for that stack. I think you'll get on a replit window, I think you'll get a couple of 100,000, maybe like 150,000 before it crashes. But it's dependent on the size of the machine, how much memory it has, and how big the stack is configured. There's actually a variable that specifies how much memory can be allocated in the stack. So just to be clear, at this point, there are hundreds of thousands of calls on the stack, some of which have completed and eventually popped back off again, but then new ones had to be added on and so on and so forth. And this is just calculating Fibonacci of 100. If you had asked for Fibonacci of many thousands, then this would obviously take way, way longer. So yeah, so we're at 153,000 calls, and so on and so forth. This will eventually crash. I'll check back in on it later. Actually, once it crashes, it pretty much just keeps crashing. So I won't actually see a final answer. Let's see if it makes it to 200,000. Okay, well, enough about that. There is a point where this will crash. You're welcome to run this code in your window, and you'll see that it will eventually crash. So I'm just going to go ahead and terminate it. All right, so back over in our slides. Let's keep chugging along here. So this was our Fibonacci. The next question that we're going to attack is, what if I had a string and I wanted to reverse the string? How could I do that recursively? So what you need to do is you need to think, okay, if what I'm trying to do is reverse a string and we're talking about recursively, then what's the base condition going to be here? So when would you know you're done? Well, if you knew that the string was backwards, then you'd know you're done. But that's not really a good base condition, because if you know that the string is already backwards, how would you know that? Like, there's no method for saying, is the string backwards? So probably the answer is, if there's nothing left in the string, then we're done. So if you give me a string that has nothing in it, or a string that has one item in it, it's pretty much already reversed, right? So now, if I know that that's my base condition, then how am I going to move closer to that? Well, it means that I have to shrink the string every time I make a recursive call. And if I'm going to shrink it, then I'm probably going to pull items off the front of the string and add them to the back of the string, because that's how you would go about reversing it. So if the string is empty, we are done. Otherwise, we're going to take the first character off and stick it on the end. A little bit of code. And we're going to see this in both C# and in Java. So if the length is equal to 1, if the length of the string is equal to 1, then we know that we can just return the string, because at that point it is just one character. Otherwise, we are eventually going to return the reverse of the string minus the first item plus s of 0. All right? And s substring takes out a part of a string, and it takes a parameter which tells you where you want to do that. So it's removing everything, it is returning everything past the first character. It's removing the first one off, basically. All right, so that's the C# code. The Java code is almost identical. You also have a s.length, which tells you that. You return the string, and otherwise you make the call with substring of 1 and the character at 0. You address it slightly differently here. Okay, so hopefully that one makes sense. You're welcome to take a string and trace it out and see what it would look like, but I think you can probably see from this that that would indeed reverse it. All right, so I would encourage you to pause the video at this point and try to run one of those pieces of code on a short string and make sure it makes sense, or stick it in a Replit window and give it a try. We've talked about going through all the files and folders on a file system, and I mentioned that that would be a good example of where to use recursion. But let's take a look at some pseudocode for that. So there's some magic in the pseudocode here because we haven't really talked about file systems yet. We're actually going to do that in, I think, a couple of weeks. But let's presume that we have a directory, D, which is a folder or a directory. Those two names mean the same thing, just depends on the operating system. So what we're going to do is we're going to set the number of files equal to 0 to start off with. And then we're going to somehow count the number of files in this directory, which again, when we talk about file systems, you'll see that there are methods for doing stuff like that. But that's going to give you back all the files in the directory. Then we need to see, are there any subdirectories in there? And for each one of those, we're going to make a recursive call. So this was something that I had mentioned earlier. You're going to sometimes see a loop, and inside the loop, my computer just hates me today. Okay, I hope you're all entertained by the problems that I'm having with silliness here. All right, so inside of the loop, you are going to make a recursive call. And that might seem very counterintuitive and possibly even scary, because if the loop goes out of control, then you're going to make a whole lot of recursive calls. Stuff like this can very easily get you into trouble, but it is legitimately what you are trying to do here. So let me pull up my little magic whiteboard thingy. I say magic, and we'll see how magic it is today. All right, so to be clear, I have a directory, which we are going to call C:\\. We're going to presume that this is a Windows machine. And C:\\/ is going to have a system 32, because everyone has one of them, and a system, and a users directory. All right, the users directory might have a enda directory. It might have an administrator. And it might have a Bob, and so on and so forth. So in order to figure out how many files there are, we are first counting how many files are up here, which we'll presume that's some number. And then we're adding to that number how many files were in this, plus this, plus this. But in order to count each one of those, I have to recurse into them. So I'm going to do a little recursive call into each one of these. So that's why in my loop, I said count the ones that are local in the folder directory that I'm in right now, and then make a recursive call to count all the ones that are in each one of the directories. So you can see why you needed a loop here. The loop is what's going to tell it to do all of the directories that are in here, and then the recursive call is going to come into system32 and try to see are there any subfolders, any files in there, and eventually that's going to aggregate up to some number which is going to fill in here. And then the same is going to happen down here. So let's actually look at how it would work when we get to users, because I actually fleshed that one out. So on the third recursive call, it's going into users. So it's going to see that there are just 3 folders. We're going to assume that each of these is a folder. I'm going to put a little F there. And so what it's going to try and do is recurse into enda. And let's assume that the answer to that came out that enda has 7 files. It's going to recurse into administrator, and administrator has 107 files, and it's going to recurse into Bob. Well, Bob may also have subfolders, and those subfolders may have subfolders and so on, but we'll assume it returns 101 files. Okay, so the answer to users then is 7 plus 107 plus 101, which is 216, if I'm not mistaken. And that gets filled in up here, which gets added to the number here, and the number here, and then that gets filled in up there. So the cool part about recursion is I didn't have to write code to say, if Bob has a subfolder, then go into the subfolder and count all the things that are in there. And if that has a subfolder, then go into that subfolder and count all the things that are in there, and keep going and keep going. I just had to say recurse. Deal with Bob. Presuming that you know how to deal with one file system that is one level deep, which is what we have written code for, which is count up all the files that are in that folder that you're currently in, then asking it to do the same thing on a subfolder will just magically work with recursion, because you'll say, go count everything in the subfolder, and it will go do it, and it will either work and give you an answer, or it will tell you that there is no subfolder and it gives you a 0. Either way, you add that number in, and that tells you everything that you need to know. So hopefully that makes sense on why subfolders and recursing is a good thing. So to review all of these examples that we've talked about so far, it is entirely possible that you will have a recursive call multiple times inside of a method. That is a very valid thing to do. In this case, you will have some number of recursive calls, which is dependent on how many files or how many folders there are in the current folder. It will do a recursive call for every single one of them, which could mean at a very high level of a file system, this could make thousands of recursive calls, and each one of those could make thousands of recursive calls, and so on and so on and so on. The actual details of how many calls this made and where all of that is, that's the beauty of recursion. Most of the time you don't have to care. As long as you know how to do it for one level, you can just ask yourself to do it for the sub-levels and it will figure it all out for you. Okay, so we're going to wrap up by writing a couple of different recursive methods, because it turns out this is where folks usually have the hardest time. It's not so bad to trace. It's no different than tracing a regular method call. You're just happening to call yourself. But the tracing is actually not so bad. Again, you do need to get in the habit of actually doing the tracing, but let's talk for just a moment about how you would go about writing things. So the first question that comes up here is write a recursive method that determines how many function calls can go into a stack until it crashes. And we basically already did this, but I'll just knock it out one more time just for giggles, and I'll make it a little bit simpler. So I promised I would do things in C#, so let me start up another C# window here and create. No, I do not want to upgrade. All right, so here we are. So we're just going to make a new method. I'm going to call it public static void crash me. And I'm going to take in an integer, which we'll call count, just so that we can see how many times we called. And I'm going to say crash me count plus 1. So that's infinite recursion, because there is nothing in there that's ever going to stop that. Crash me will start off with 0, and if I run that, we're never going to get to the hello world, because my crash me is going to crash. Well, that crashed very, very quickly. Did I ever get to see the output? I didn't. Might be nice if I had actually put out a print line. All right. Tell you what, I'll only print out every 100. So if count mod 100 is 0, then do a print. So this will just print out 100, 200, 300, so that I can see how far in I got. This won't give me an exact answer, but it will give me something. Okay, and I think that scrolled off the screen before I was able to actually see it. Tell you what, let's do it every 1,000. I just need to hit stop when it actually crashes. I need to stop pressing stop so quickly. I get excited when I see output. Okay, well, I think we actually did get to see the answer that time. I think it was 500. It was right up at the top. Maybe, maybe not. No, we didn't get to see the answer. I think it's basically when it pauses, because that's when it actually runs out. So it looks like it got to about 521,000, give or take. Please note I'm only printing out 1,000, so we know it's less than 522,000 calls onto the stack before it crashed. The more stuff that I put in here, the sooner that will happen. So I'm going to say long x equals 100L, I guess just 100. All right, so it used to be 521,000. Let's see if that makes a difference. It did not make enough of a difference. So let's do this. Stop. The reason I'm doing this is because each one of these takes up some amount of space. Now, I grant you it's a small amount of space. Actually, let's do this. String just typing random characters because that will take up more space. There's already an X. Good. Now there's an XY. 521. Okay, well, I can't make it happen. But my point here is that there is actually space allocated each time. And when you make more and more variables and you put bigger things in there, you will eventually cut down on the amount of space that you have in the stack, because all of these variables exist in the stack, and they will eventually lower the number of times that you can make entries, because the stack size is set. The number of times that you can recurse into it is determined based on how big of the stack memory is. The more things you have in each one of those recursive calls, the faster you will run yourself out of stack space. So hopefully that makes sense. All right, so let's move on to the second example here. Imagine an array of numbers. Can you use recursion to sum them up? Hint, the sum is the array at position 0 plus the sum of the rest of the array. All right, so we're going to go back over to our replit window here, and we're going to start off by defining an array. So int my array gets new array. Let's say new my array. We'll do 10, and we'll go ahead and preset it. 2, 4, 6, 7, 8, 9, 10. All right, we're not going to call crush me anymore. What are we trying to do here? We are trying to find the sum. All right, sum array. All right, we're going to have to pass this my array, and we're going to need a new method up here. All right, we're getting back a sum. Okay, so how are we going to do this? Well, we know that if the only thing in the array is the first cell, then we're going to return that number. So somehow we need to know where we are in the array. So the simplest answer there is to start off with a variable that points at cell 0, and then keep incrementing that every time that we move down the array. So I'm going to pass in a second parameter. Also, I'm going to make this one be a correct parameter. All right, so the second parameter is going to be the position that we are in the array. So that's going to be an int. All right, so in order for that to work, we have to start off with a 0. Okay, or maybe we start off with the length of the array. Do it either way. I'm going to pause for just 1 second, folks. Sorry. Okay, so as I said, we could do this one of two ways. We could either start at the left side and add all the numbers to the right, or we could start at the right side and add all the numbers to the left, and it will work either way. So the question that we have to decide is, which one do we want to do? And I think the answer is, what we're going to do is we're going to start off passing in the size of the array down here, which is going to be known as, first off, that's supposed to be an int. Sorry about that. Okay, so we're going to pass in the size of the array, which is called myArray dot get length. All right. So the position in the array then is going to be all the way at the end. If we get to position 0, so if position equals 0, then we are simply going to return myArray at position 0. All right. In every other case, we are going to return the current cell plus a recurse one less. So that's going to be myArray at position plus SumArray at position -1, because we're going to move in a little bit further. All right, so the only trick here is that getLength is actually going to return the real length of the array, which is 10, but there are only cells 1 through 9. So I'm going to put a -1 on there just so that that comes out to 9. So it's going to say, if we reach position 0, then return that. Otherwise, return whatever's in cell 9 plus the sum of everything that's in cell 8. Okay, so we're going to run this, find all of my syntax errors, of which there are many. Wow. What did I do up here? Where did that come from? Okay, line 14, we have an unexpected, and that's because I forgot a semicolon. And we have an unexpected symbol L on line 13. Yeah, because that's not a semicolon, that was an L. All right. And we have an unexpected symbol SumArray on line 19. And that's also because of a missing semicolon. Okay, now, it would have been wonderful had we actually printed out the value. It would be wonderful if I actually captured the value. Int answer equals, and then we're going to print out the answer. Okay, so I'm sure that's probably right. We'll just cheat and make these all 1s, and then we'll know what the right answer is. It's a good way of debugging. I think that was 10 of them. Any bit of luck, that'll give us the number 10. Hey, look at that. Okay, so how do you go about writing this method? The answer is, you try to figure out what the base condition is. I fully acknowledge that this is kind of a silly example because it would be easier to do this with a loop, but it is possible to do it either way. The answer was, first figure out the base condition. The base condition is that we are looking at an array that only has one element in it. If there's only one element in it, the sum of the array is that number. Now, you might say, but what you're passing in is always the entire array. So what do you mean an array that only has one element in it? And the answer is, I'm using this position to mark where I am in the array. And this is a pretty common thing that you will do inside of recursion. You may need to pass in a second parameter that keeps track of what you're doing. And you're going to see this again in just a moment when we do the third example. So what you're doing here is you're saying, if the position is 0, i.e. you've reached all the way to the front of the array, then at that point return the array of 0. If you were given an array that had only one item in it, i.e. there was just something in position 0, there was an array of size 1, then this would work great. It would just return the answer. In every other condition, what you're doing is you're taking the value of the cell that you're currently looking at, which is denoted by the position, and that is myArray at position, which in the beginning is going to be the number 9. The position is going to be 9 because that's the length of the array here. So it's going to take the value that's in the 9th cell, cell number 9, and it's going to add that value to the sum of all of the other ones, which we don't know the answer to that yet because we're going to have to recurse. When we're making the recursive call, it's super important that something is moving you closer to the base condition. Our base condition is the position is 0, so I better be decrementing the position so that I'm getting closer and closer to it. You could absolutely have written this the other way around. You could have passed in, instead of position 9 in here, you could have passed in position 0 and then worked your way up the other way, in which case you would end when the position is equal to the get length minus 1, and at that point you would return what's in get length minus 1, and in every other case you would recurse closer to it. So hopefully that makes some sense. All right, so the third example that they want us to do here is imagine an array of sorted numbers. What is the most efficient possible way that you can see if the number 45 exists in the array using recursion? All right, so we're going to start off and we're going to talk about guessing games in general. So I'm going to pick a number and I'm going to put it in my head. So I'm going to say that the number is between the numbers 1 and 100. Okay, so I want you to guess what the number is. I'm going to write it down on this piece of paper over here that I have next to me. Okay, done. Now, guess. All right, if you're playing this game as efficiently as you possibly can, the correct answer, assuming that I will tell you whether you're too high or too low, is to guess the middle number. Because if I tell you too high or too low, you get to eliminate half the choices. So if you guess the number 50, and I say that that's too low, you now know that it is not in this half, i.e., it is not 50, because I already told you it's not 50. I would have told you, yes, you got it right if you had guessed it correctly. And I told you that the number you gave me is too low, so therefore you know it is not the number 1 through 50. All right? So that means the only possible choices at this point are 51 through 100. All right? So now you need to guess again. Well, the correct answer again is to guess the number in the middle, which is going to be the number 75. All right? As I look at my number to remember what it was, I'm going to tell you that is too high. Cool. So now you know it is not from 76 or 75 to 100. So the only possible numbers at this point are 51 through 74. All right, so again, you need to guess the middle. Well, how do you calculate the middle? You add these two numbers, 51 and 74 is going to be 125, and you divide that number by 2. I'm just going to use a calculator because I'm feeling lazy. I think that's going to be some number. 51 plus 74 is 125. I got that right at least. Dividing that by 2 is going to be 62. All right, 62 is your new guess. All right, and I'm going to tell you that that's too low. So at this point, you know that the number is between 51 and 60. I'm sorry, it was too low. I did it wrong. So you now know the number is between 63 and 74. All right, halfway between 63 and 74 is going to be 137. Divided by 2 is going to be 68. And so we're going to go back over here. 68 is your new guess. And I'm going to tell you that that is too low. I'm just going back to the previous screen. We had 63 to 74 was the previous range that we knew it was in. 68 was too low. So that means that it is somewhere between 69 and 74. 69 and 74, adding those together. Isn't this the funnest game ever? You get 71. All right, and I'm going to tell you that is too low. At this point, we're down to 72 and 74. And at this point, you're going to guess 73, and I'm going to tell you that is correct. Ta-da! Funnest game ever. Don't you just want to go play this with your friends and family? You're in quarantine. What else are you going to do? Okay, so what is the point of this? We got to the correct answer, and we got to it in, it looks like you guessed 1 time here, 2, 3. I know you're saying I guessed these. 4, 5, 6. So I gave you a range of 1 to 100, and you guessed on attempt number 6. No matter what number I had picked, you would have gotten it in about 6 or 7 tries. Why? Because you're doing it the most possibly efficient way. What is the least efficient way you could have done this? Well, you could have said, is it 0? No. Is it 1? No. Is it 2? No. Is it 3? No. In which case, it would have taken you 73 times, assuming that you started at 0. If you'd started at 100, you might argue, well, okay, yeah, you would have gotten there in 27 turns, and that's true, but on average, it will take you 50 tries to get any number using this method, because on average, you'll get there about half the time, assuming that things work out for you. So 6 is a dramatic improvement over 100. So this is called a binary search. You are trying to find a number, and every single time you are throwing away half of the choices. This can be coded relatively easily, so let's go ahead and code it, because, it'll be a good example. So to be clear, I'm going to give you an array of numbers. The array of numbers is guaranteed to be sorted, so I better actually make an array of sorted numbers. All right, so we have 1, and then we have 4, and then we have 9, and then we have, 15. Don't jump that much. 26, 34, 42, because that's the answer to the world. 2, 4, 6, 7. And 100. I believe that is 10 numbers. 2, 4, 6, 8, 10. Great. Okay, and this time we are going to return a Boolean, and the Boolean is going to be found or not found. And we are going to call is in array. We're going to pass our guess. We're going to pass the array. All right, and this is going to be some kind of recursive call. And then we're going to get rid of this, and I'm going to say if found, then console write line, yay. Otherwise, boo. Hey, we have a Halloween theme. Boo. All right, great. So we now need to write our method, which is going to be public Boolean is in array, which we said takes in our guess, which needs to be a number, our array, which is an integer array. Okay, now we're again trying to think through how we're going to do this. So it seems to me like the obvious answer is if the guess is at the current cell that we are looking at, then bing, we have it. So let's talk about visually what's going on here. So I have an array. Okay, sure, that works. I have an array that has 100 cells in it. Perhaps in this case it has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Isn't it great how you can always subdivide the last one? All right, so this is cell 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So my array is actually 10 cells long. We know that because I defined it, I hard-coded it in the code as being size 10. But virtually, the space that I am looking in to see if I have found it is also 10 right now. So what I'm going to do is I'm going to use two more integers. I'm going to call one of them start, and I'm going to call one of them end. And what I'm going to do is I'm going to set them to the ends of the array, one extreme and the other extreme. And then as I look to see, did I find it, then I'm going to return back yes or no. And if I have to recurse, I'm simply going to move the start and end positions. All right, so let me fill in the numbers that we have here. This is 1, 4, 9, 15, 26, 34. I have a brain like a goldfish. 42, 62. My little cells are going to hurt me. 73 and 100. Yep, that's totally 100. Okay, and the guess that we are making is going to be, I'll put it in red, we're guessing 73. So what we're trying to find is 73 one of these numbers that we have? And we're going to do this recursively. So based on all of this, and let me just put my guess in because I actually think I never did that. Int guess equals 73. Great. So we're passing in our guess of 73 and we're passing in the array and we're trying to see, is it in the array? The most efficient way that I can possibly do this is I can look at the middle of the array and I can see if in the middle of the array that is the correct answer, i.e. is there a 73 in here? If there isn't, then as long as I can tell whether it's greater than or less than the number that was here, that will tell me whether one side of the array, which is this bit, has it, or the other side of the array, which is this bit, has it. Right? Because I can tell if it's smaller, it's in this side. If it's larger, it's in this side. So all I'm going to do is I'm going to adjust my start and end positions to line up with one of these two choices. All right? So let's begin in code. The win condition is they gave me a guess that is the cell that I'm currently looking at, which is this middle cell. So I'm always going to have to calculate where is the middle. So I'm going to call int middle, and I'm going to set it to be start plus end divided by 2. That's going to be the middle. This presumes that I'm taking in a start and a end. All right, which means that down here I have to push in my start, which is going to be 0, and my end, which is going to be my array get length. That is totally not how you do it in C#. This is totally C#. What language am I in? Who are you people? It is going to be, oh, you know what? Let's just cheat. Say it's 9. But yeah, it is my array. Like that. All right. And where are you complaining about? Line 15. Oh, wow. If found, I never closed that parenthesis. Not all code paths return an answer. That's fair. Okay. So we calculated a middle. If my array at middle is equal to the guess, then we're going to return true. Great. So if it's in the array, we return true. Otherwise, we got a lot of work to do. So one thing that we need to know is, when is this recursion going to stop? We can't rely on this first clause to stop it, because they may ask for a number that is not in the array, in which case that's never going to happen. So something else in here has to be the case where we know it's not in the array. So if we go back to our picture, and we presume that we're going to go and make these recursive calls, there will eventually come a point where I am no longer able to search anywhere, because I know that it would have to be higher than my end and or lower than my start. Or to phrase that another way, my start and my end would have reached each other. So I'm going to write the recursive call first, and then I'm going to come back and write the terminating condition, which is a little bit backwards, but I just want you to see how you might work this out. So the recursive call is, I'm going to say is in array. I'm going to pass it the same guess, that hasn't changed, the same array, that hasn't changed. But there's two different possibilities. So if the middle is greater than my guess, then I need to do one thing. If it's less than my guess, then I'm going to need to do something else. So to be clear, we've looked at this middle position and it is 26. 26 is smaller than, we're doing the flashy thing again. 26 is smaller than my guess, which is 73. So therefore I know that it cannot be in this side of the array. You agree? The number that you guessed, 73, is greater than the value that is in this middle cell. So I'm going to write it like that just so that it's a little clearer. If the guess is greater than the number in the middle cell, then I need to call myself passing it these cells over here. Because I know it can only be in those cells, if it exists at all. So my end is still going to be my end, but my new start is going to be here. And how is my new start going to be here? Because I know it's not in the middle cell. I would have returned true if it was in that one. So I know it's over on this side. What is this? It's middle plus 1. So my start is going to be middle plus 1, and my end is still going to be end. And I need to return whatever that gives me. Okay, so hopefully that makes sense. So if the number that you're looking for is greater than the middle of the array, then we're going to return the right-hand side of the array. All right. Otherwise, and I am going to put in my curly braces here, just bear with me. I'm writing this in a really weird way just to make sure that you guys understand what's going on. I'm doing it the way you would probably think through it rather than writing it all out in one fell swoop. Otherwise, then it must be on this side of the array. So this side of the array, the start position hasn't changed, but the end position is going to be middle minus 1. Because again, we know it's not in middle, so therefore it's the array from here to here. And that was the case where the guess is not greater than the one in the middle. Okay, so life is good, except there's nothing that's ever going to stop my recursion. If I run this right now, this is going to go forever and ever and ever and ever. So how do I stop the recursion? Well, if I ever get to the point where my start and ends have switched places, then we know something is wrong. Let me give you that example. So we know that after our first call, we moved start to 5 and end is still at 9. On our next call, we're going to calculate the middle between 5 and 9. 5 plus 9 is 14, divided by 2 is going to be 7, so this is my new middle. All right, we're going to look at the number that's in here. 62 is less than 73, so we know that it's not in any of these. So I'm going to pass a new start that is 1 plus the middle and an end. That's 8 and 9. 8 plus 9 is 17, divided by 2 is going to be 8. Is that right? 8 plus 9, 17. 17 divided by 2 is going to be 8. Yes, that is correct. So my middle, weirdly, is going to be in that same cell. And at that point, this is going to return true. So if I run this code right now, it is actually going to work. But it is only going to work, bizarrely, because the number that I'm searching for is actually in the array. So if I run this, it will return true, yay, which is what it was supposed to say. If found was true, then it returned yay. But now I'm going to go search for a number that is not in the array. I'm going to search for the number 63 or 763, whatever. And we're going to run it, and you're going to notice it is not going to return. As a matter of fact, it just crashes really terribly. Why did it crash really terribly? Because it actually ran out of memory. It happened very, very quickly because I'm not doing any print statements, but it made thousands and thousands and thousands of calls that were recursive, and eventually it just crashed because there was no more memory left. Now, how do we stop this? So, if you see something like this, you have reached infinite recursion. The reason that that happened is because when it was looking for 73, can I back up until I get back? Oh, that's awesome. I have undo on my whiteboard. How cool is that? Okay, I need to get out more. I think that's very clear. Okay, so let's go through this example. We are now looking for the number not 73, but instead we are looking for the number, I think we asked for 63. Is that what we asked for? What was my guess? Guess equals 63. All right, so we're going to follow our code. So we calculate the middle, which is the same as before. So it's 0 plus 9 divided by 2 is 4, so my middle is here. Is 26 greater than or less than 63? Well, 26 is less than 63. So I'll say that the other way. Is 63 greater than or less than 26? 63 is greater than. If guess is greater than my array at middle, which it is, then we are going to make a recursive call passing in middle plus 1 and end. So this is my new start, and that's my new end, and that's going to be my next recursive call. Okay, so this time start is equal to 5 and end is equal to 9. 5 and 9 is 14, divided by 2 is 7, so my middle is going to be here. Is 63 greater than 62? And the answer to that question is yes, 63 is greater than 62. So it's going to make a call with middle plus 1 and end, which means that my start is going to be 8 and my end is going to be 9. Okay, so in this next recursive call, it's going to try and calculate middle. 8 and 9 is 17, half of that is going to be 8, so my middle is this same cell. So this was the condition where it ended last time because it found the number that we were looking for. But this time it looks to see, let's follow the code. Calculate the middle, which we just said is going to be the number 8. If the middle equals the guess, if the number in here 73 equals 63, it does not equal that, so it goes in and it says, is the guess greater than the middle? So is 63 greater than 73? It is not, so it's going to go to the else, and it's going to make a recursive call for start and middle minus 1. Well, start, in this case, is 8. So this is our start. So middle minus 1 is actually going to be 7, which is here, and end is still going to be 9. So it makes a recursive call with 7 and 9. It's actually gone further away from our end condition. Why won't that blinking stop? There we go. It's gone further away from our end condition. In the next recursive call, it's going to add 7 and 9, which is going to be 16, half of that's going to be 8, and it's going to move the start back to 8. In the next recursive call, it's going to move the start back to 7, and the next recursive call, it's going to move the start back to 8, and it's just going to keep going and going and going and going. The reason that we knew something was wrong was when the end had gotten past the start. If that's ever the case, where your end is less than or equal to your start, then you know you're done. So let's add in that circumstance. So if the start is less than or equal to the end, the other way around. If the end is less than or equal to the start, then we are going to return false. So we got boo because it is no longer working. So 63 is not in the array. Let's try it again for 70, or 42, I guess, something in the middle. And 42 says yay. Let's try 43. It says boo. Let's try the number 0 all the way up at the end. These are the fringy conditions you might want to test to make sure that it always works. We're going to put in a number that's greater than the right-hand side, 101. It says boo, and so you have a search. And how many times did it actually have to make a recursive call? The answer is probably 3, because call 1, call 2, call 3, call 4. It was on call 4 that it decided it's not here because the start and ends had gotten past each other. And I'm just going to also print out the start and end conditions. So yes, the end condition. All right, and let's run that. Okay, so we started with 0 and 9. We moved to the midway point, which was 5 and 9. We moved to 8 and 9, and then we moved 9 and 9. Start and end had reached each other, and at that point it exited because it has reached the end of the line. So hopefully that makes sense about how to go about writing it. I gave you logically how I would go about solving this problem, insofar as figure out the conditions that you would need in order to move around inside the array, and then figure out when you are done. Those are the two things that have to happen. You might say, this start and end thing that I came up with here is not intuitive. You might never have thought of that. And you're maybe right about that. It is not overly intuitive. There has to be some method for you moving around in the array. If there was an easy method for slicing the array in half and only returning half of the array to one side, then that would be a much better way of doing this rather than tracking it. But arrays aren't easily divisible by that, like that. So there's no good method for saying, just give me an array that's half the size of the other array. So using the start and end was the trick for doing that. And you will see that it's not uncommon for people to use start and end conditions or counters when they're working through recursion. The print statement that I added here at the end is a useful tool as well, because it allows you to see what's actually happening inside of your code. How many times it's getting called, what were the start and end conditions. That will allow you to debug. It's the same as tracing it on paper, it's just that you're getting a little bit cleaner. So let's make this array a lot larger, and let's see, how can I do this? We're just going to put in a loop here. Some random garbage in the array just so that I have an array with 100 cells in it. All right, and we're seeing if 101 is there, which it should not be, because, well, actually it probably will be. Let's see how often this gets called. Come on, Replit, you can do it. Program's already running. Okay, so now with a much bigger array, you can see it started at 0 and went to 99, which then gave it 50 to 99, which then gave it 50 to 73, which then gave it 50 to 60, 50 to 54, 50 to 51, 51 to 51, and now it is not there. So we can tell that the number 60 or 101 did not end up in this array, and that kind of makes sense because what should be in there is 0, 2, 4, 6, 8, 10 up to 200. So if I put in an even number like 14, that should be in the array, and we'll see that it'll find it there without too many problems. There it is. It turned out it was in cell 57. And even if I make this a much, much larger array, so now I have 100 or 1,000 cells in there, you can still see that this works very efficiently. I got to my answer in 8 calls, and my answer was yes, it was in there. And even if I give it something that isn't in there, I'm still going to get there in 10 calls. Turns out that the answer is about the square root of the number. So if there is 1,000 cells, it's the square root of 1,000 is about how many times it's going to take to get there, which is just a weird math property. And if I have a square root button, which I think I do over here, guess you do this the other way around. Who knew how to use a calculator? All right. Yeah. Well, you get the idea. So worst case, it will be 31 calls. All right. Okay, so recursion. In summary, you are always going to have 2 things. A base condition, which is what actually makes the recursion end, and a recursive call, or maybe multiple recursive calls, that is going to move you closer to the statement or to the base condition. You will always need to have those 2 things. If you don't have those, you are not doing recursion correctly. And then with regard to how to come up with a recursive function, you need to figure out what is the base condition and write that, and then you need to figure out how to move closer to it. And you're always going to be stating the problem in a way that is similar to how do I get one step closer to that? How do I look at a smaller version of it, etc., etc. So hopefully this clarifies recursion, and if you guys have any questions, this is definitely one of those topics that it all makes sense when you listen to the lecture. You really need to try coding things in order to get it. You'll get some examples in your labs this coming week. You'll have some examples on the quiz that'll come up here, but this is definitely one of those things that will be on the test, and you guys need to get used to doing stuff recursively and know how that works.